Have you ever wanted to control all the LEDs from your computer with one software? Today I'm going to try to show you how this is potentially possible with a lot of products that are out there. Your motherboard, your graphics card. I won't go into like mice and other things, but this is really focusing on the motherboard and the GPU. A couple months ago I did a little demonstration on how to control your RGB through like one software, and I used this little mock-up right here, of how to do it. And I got a lot of questions. People wanted to know how exactly I did this, you know, give them tips and whatnot. And I'm going to do my best to do this. I mean, this is kind of complex, and I would highly recommend that you do this at your own risk. I do not provide any warranty through this. I am not a professional electronic engineer. I'm just a hobbyist. So I learn as I go and learn from my mistakes. So I'm going to show you things that I've learned, and if anybody knows more than me, feel free to speak up and correct me if I'm wrong in any place. So right here we have an I/O shield that actually has RGB integrated, and a motherboard kind of larger than monoblock that has addressable LEDs, and this just has analog LEDs. And I wanted to show you guys how I kind of figured out, you know, what type of LEDs, what technology goes in this, what voltages and whatnot. So let's begin. This is a Z390 Waterforce Extreme motherboard. It's by Gigabyte, and it's on loan to me thanks to ModMyMods. Unfortunately, it's dead. I didn't break it. It was on their wall of motherboards where they just kind of hang it up, and fortunately this one died, but they're nice enough to give it to me so I could test out the LED headers, and also this motherboard was provided by Gigabyte to them, so indirectly thank you Gigabyte for letting them have motherboards so I can play with it if they die. So the goal today is to try to find out like what type of RGB LED headers we're dealing with. We have a LED header here, right here, one here, one here, and another one on the back side, and I'll show that to you in a second. A couple things you want to know. We want to first decipher whether this is digital or analog. Digital has that addressable, that kind of sequenced marquee look, that rainbow effects that you can get, while analog is just kind of like one zone will be one color. And what we're going to be doing is we're going to see what we're going to first find out like what type of technology does it use. Does it use addressable / digital, or does it use analog? Then after that we have to look into voltages, see what type of voltages it uses, and so I guess we can begin. So right here I have a multimeter, and I'm going to use this as a tool on how to figure out what is what. So I did a little video on how to use a multimeter for LEDs, and you can check that up right here, somewhere here or here. And we have it set to continuity, which is this little like speaker or Wi-Fi signal right there. And what happens is when I press the little leads together, it makes a little beep noise. And that's how we kind of figure out what's connected to what. And that's critical because we're actually going to use the addressable LED header, primary addressable LED header, to find out what is what. And the most important part is finding ground. So like if I move the motherboard this way, so a lot of places, a lot of things connect to ground. So we have the I/O, then even these little around where the screw goes, we have ground points. So a lot of places are grounded on the board, and that's one good thing to know. So that's kind of that's one thing to keep in mind. So addressable LEDs will always have a ground point, and that will always be connected to every other ground point. And analog won't. So that's kind of one way how we can figure out whether it is digital or analog. And we're going to use the digital LED header right here to figure out what is what. So what I'm doing is I'm writing the silk screen where it matches the header. So a lot of these have like the silk screen, which will be white usually if your board's black. And I wrote like kind of where the pins are, how it's oriented on the board itself. That way it makes it easier to kind of document which pin is what. So for this, I'm going to first put my, where am I? Okay, there I am. So what I'm going to do is, I know this is an LED right here. I'm going to touch different parts of this. Hey, I hear continuity. Wait, that went away. Oh, I hear good continuity there. Okay, I'm holding it there, and that is ground. So we know that that pin's ground. So this pin right here is ground because the board is reversed. I mean, maybe I should actually go do this. This might be easier for you guys because the way this is orientated, yeah, whatever. So I decided to flip the board around to make it easier for you guys. So I have two headers right here to match up to these two headers. I have this header to match up to this one, and this one goes to that. So I mean, it's pretty easy. What it happens is you remove the chipset, you remove the I/O, and what we're doing is we're taking control of the LEDs that are actually connected via cable to the board. Like there's other LEDs throughout the board, like on this board, like right over here. These look like LEDs, and we can't really control those with another software. So best way to do is just disable those and then control everything that you have plugged in. You know, that's my opinion the best way to do it. And that's kind of what I'm going to cover. So we're going to do is we're going to map out everything and see what everything is. So first thing is first, I'm going to get I'm going to attach it to a ground. I'm going to use, you can use like, use the ground right here for the digital LED. And I'm going to find where ground is. So what I'm going to do is I'm going to find the ground. So bottom two, nothing. Middle, I think I hear something. Hey, why did that go away? I wonder. Hey, that one also has continuity. That one doesn't. So we hear continuity here, and that's a nice long thing. But I thought I heard continuity over here for a second. Let's try that again. Oh, that went away. So what's going on here is we just identified both the ground and the voltage. So if we check continuity between these two, between voltage, okay, I have continuity between that. And reverse, hey, I get ground. Continuity between both of them. So what's happening is you have what are called decoupling capacitors, and they connect to the 5 volt or 12 volt voltage and also ground. And there's a few different reasons that they use them. And generally you have one next to every integrated circuit. But so what's going on is when I'm checking for continuity, it comes on for a split second because of a little bit of continuity, and then what happens is the probes charge the bypass or decoupling capacitors to the point where there's resistance. So what you'll see on the multimeter right here is just testing to see if they're connected to each other. So I'm ground, and I'm going to, as you can see, the resistance is rising. And if I test, so I can indicate that's ground, and I know this is voltage, and I can also do continuity test between this pin and also voltage, and hold it there, and I have voltage. So that's a good way how we can test out what is connected to what. So we know this pin is ground right here, ground. I'm writing upside down, and then voltage was, I think, right here. Yep. This is 5 volt. We'll just do plus V. I can't even do an upside down 5. I won't even try. So we know that's the voltage. So this one's a little bit more complicated. There's 6 LEDs here. I mean, sorry, they're not 6 LEDs. There's 6 connectors right here. And this is kind of a weird connector, and it took me a little bit of figuring out to try to see which one goes to what. But luckily on the connector itself, it has 2 pins missing, and this pin was removed by mod. So that leaves me with the red wire, which is data, which surprisingly is data in this case because there's 3 pins missing. We know what ground voltage is, so therefore that 3rd pin right there is data, and that's data in. So we'll put DI data in. So we've mapped that out. So now that's how I was able to have it kind of glowing like that. So let's check a couple other things around here. So let's move this board forward. And I see two LED headers up here. Let's map them out. If I can get a hold of my leads. So I just use this as my kind of ground reference. So LED cover, let's try that. LED cover. So same. Okay, top one, I'm getting solid continuity. Bottom one, the bottom one, I'm seeing. Let me show you. I'm seeing the resistance start to climb. So let's try. Okay, it's connected to the 5 volt. So we know this top one, this top has ground right here. Ground is there. We know it's plus voltage right here. But we have, so that this has to be a addressable, even though it has four pins. Well, some people get confused. Why does that have 4 pins? Well, the answer to that is that this has a data in and data out pin. So that way it can pass it onto another portion of the motherboard. And we can test that out at a later time, but one of these will actually be data in and the other one will be data out. I mean, I can try, let's see if I have continuity between any of these. No continuity there. Let's try continuity here. None there. So the data in or out is either not connected to that side. I'm actually going to flip it over really quickly just to test this side of the board. So test this right here. And I know you guys can't see stuff, but so I'm not seeing any continuity, so I don't know why exactly why they have that 4th pin there. So I think I did see a couple data outs on this. Let's try this. No continuity. Let's see if I can find another one around here. Yeah, I know you can't see stuff, but you know, this is not really easy to hold and do this type of stuff. So I'm just doing a test for myself. And yes, you can't see it, so I'm going to just test for continuity between that. Nope. Hey, look. So the back of the board is connected to the front of the board. Right there. So I guess the backboard is connected in series to this monoblock, which plugs into this. So that is kind of interesting. So let me get back to my little mapping right here. So data in, and I don't know what this is until a little bit later. We'd have to test it out physically, or test it out, and header, but the board's dead. And on this board, this is the extreme, the Water Force edition doesn't have anything that plugs into this. It only plugs into the LED I/O, which we're going to test next. So we have 2 question marks for these two. One could be just not connected, the other one could just, or it could be connected somewhere else in the board, who knows. So next thing we're going to check is for this next little header right here. Okay, there's no continuity right there. And so if we're not showing continuity on ground, if we're not showing continuity anywhere on a header, and it's for LEDs, then we have a good indication that that's going to be an analog. So this one is going to be analog. The rest, the other ones that I've checked so far are digital, which I'm not surprised, because if you watch any videos on a motherboard, you'll see like the addressable like kind of effects that are going on. So we'll come back to that one. So next we're going to try this one right here, which is a PC chipset. So let's look for ground. Yep, that's ground over there. Let's check for voltage. This one. So therefore I know that ground will be right here, and that this is also digital. So this will be ground. And this will be plus voltage. And we know it's 5 volt, and this is also digital. So yeah, I know this might be a little hard to see, but and figure out. And most motherboards I see don't have lighting on the back. This motherboard has a little RGB LED kind of strip in the front that connects to the bottom header. and we're going to map that one up and figure out what it is. So right here I noticed these pins, and I know this is kind of the weird form factor that addressable LEDs have from the backside, and you can also flip it over and compare it. So I know this is going to be ground, and so I'm going to look for ground over here. Yep, first try. Yep, and that's voltage. So ground is this side and voltage is this side. So what I'm going to do is I'm going to mark that. So ground. Oh wow, that's the worst upside down ground I've seen. Plus voltage. So we've mapped out the voltages, and some of the boards might come with just 3-pin addressable, but these are 4-pin. And sometimes when you have the addressable LED, you might have a clock, but I haven't seen that on motherboards. I've seen it on like a sound card, an EVGA sound card that has clock on it, which makes it which uses a different technology than the WS2A2B or whatever LEDs. I can't even think right now. Anyway, so we've mapped up those pins, and we know this is analog. This right here is an I/O, and I know this is LED I/O, so that means that this is analog. And most of the LEDs, at least analog LEDs I've seen on Gigabyte's motherboards, in regards to the onboard, I've seen are 5V, and one way you can tell is if the lighting's on when the PC's off. Well, you can tell that's 5V because only the 5V standby rail is on when the PC's off. So that's one good way to tell if it's 5V or 12V. And when it comes to using analog LEDs, there's less risk for like reversing the polarity. And I have this little connector that I have right here, and I have a little power supply right over here. And what I'm going to just do is plug it up onto this, plug it up to it. Let me turn this on, and I can map out the colors this way. So let me flip this over this way. It's usually probably not the safest way to do this, but oh well. Again, I'm not a professional. So, okay, that's blue, that's green, and that's red. So, most likely this is 5V. Hopefully it is. And I don't really want to open up the I/O shield to tell. But and some of the other Gigabyte devices, they use 5V, they don't drop it down. So if you notice that in this order we have RGB, which is the pinout. We have this I/O shield, and now we're going to see how it connects to the motherboard. So the way it connects is the voltage, which is the light gray, is down. So what we're going to do is I'm going to label it, which I just did. So 5V RGB. And the issue or the problem that you might see here is, if you know about anything about the 12V analog headers, it's GRB, not RGB. So in order to kind of hack this, we'd have to swap the two pins around. But I mean, that's really it. And I hope this is 5V. I mean, but I'll show you kind of how we can figure that out. We mapped out that. We mapped out the voltages, the data in it, so we know which ones are the data. I mean, that's kind of really it with, like, trying to figure out what is connected to what on the motherboard. I mean, you just have to use a multimeter, and I mean, there's a couple of other ways you can tell. Like you have to look at the LEDs themselves as another way. So here I'm going to do kind of a little demonstration. So right here is kind of the I/O cover for my Z370 Gaming 7. I already know that this one is, and I actually just tore this off. That's why it has like this is from the mock-up I did. But I'm going to remove the little LED strip from the back, and it's actually a little PCB that connects to the board. And I'm going to show you like kind of how to figure out what LEDs are used. Like in the Gigabytes, it seems like they use 5V for the analog. I mean, again, like this is not something that's really this is not something that's really a standard as far as, you know, because they can change between motherboard revisions and whatnot. But so looking at these LEDs, I see there's 2 LEDs right here. They're connected, and I also see that there's 6 resistors. So when you see, since there's 2 LEDs and 3 resistors, that means we have 1 resistor for each LED, and each one of these resistors are actually for the for red, green, and blue. And I've showed in a previous video how to use like the Diode Tester, so let's see if I can figure this out. Yeah, you can see that. So I'm using a forward voltage, and it's telling me it uses each LED, and I'm bypassing the resistors, so it's telling me how much voltage is dropped or used by the LED. So white is using 1.6, or sorry, red's using 1.6, blue's using 2.4, and green is using 2.15. So what you do is you write down the numbers, and then you also figure out what the resistance value is, and you write them down. Select. I'm taking a continuity mode, so this is 100. So you try to map out everything and figure out like what is connected to what in terms of like the LED. So we need to figure out, okay, where's this resistor connected to? So a lot of this goes into like how the circuit is set up. So that's for the green. The green's up there, and you would write this down. I'm just doing this for a quick demonstration. Okay, this is connected to blue. This is by red. So then what you do is you write it down where it is, and then we know that there's 3 resistors, and you get the resistance value, and like, you know, if you plug up 150, that's red, it's probably going to be 100, 100, and 100. And so there's calculators on how to figure this out online, but we're looking at 200 resistance value resistors right here, one for the green, one for blue, and red always generally has, you know, a higher resistance value for its resistor because it has lower voltage required to power it on. So because these resistance values are, you know, 100, 100, 150, these are going to be, I know these are 5 volt. If it was 12 volt, the resistance value would be much higher. And for example, in this like Gigabyte graphics card actually does have a 12 volt single LED in there, and it has higher resistance value resistors in it, but there's only one because I can't take advantage of what's called the voltage drop throughout the LEDs. So if you have one LED and you have like 100, 100, 150, then it's going to be 5 volt. If you're going to have, you know, much higher values than that, and it's only one LED. So right here we have a strip, and as I showed in my other video, we have 3 LEDs in series, and this strip right here and this strip are actually wired in parallel, but all the LEDs on each portion is actually in series, and we have one LED for each of the colors. Sorry, we have one resistor for each of the colors RGB, and that's a current limiting resistor. And depending on the supply voltage and how many LEDs that we have wired in series, it's there to basically prevent the LEDs from eating too much current and blowing up. So, for example, we have a supply of like, you know, 12 volts. We're going to test out the strip right here and just do a quick 4 voltage test. So let's get a higher number like green. So 2.2, and what's blue? 2.5. So what we're going to do is do some math here. So we have a 12 volt supply. We know these LEDs take 12 volt. We know the blue requires 2.5 volts because they're wired in series. We combine them, and it goes up to 7.5 volts. And that's required to light these LEDs up. And then we use the resistors to limit the current, how much current produced. So we can't use like a 5 volt because it would be very dim. I mean, we can try that and see what happens. Let's give that a shot. right here I have adjustable power supply, and I have it connected to I have the voltage connected to this one, and what I'm going to do is I'm going to see. You can barely see. I don't even know if you guys can see it. So red is lighting up just a tad bit, and so you can see it can't take. It needs more than 5 volts, and that's because red uses, you know, quite a bit less, so it's just barely enough to put it on. So I'm going to go up to 12 volts, set this, and so as you can see, so that's using 8 volts, that's using 6, it's using 8. So as you can see, even though okay, you're seeing right here is we have 12 volts, I mean almost 12 volts, that's what the supply is. And when I connect this little lead right here, you can see it drops down to 9. This is 6. And this is 8 volts. So the blue, as I kind of did it, you know, 7.5. So 8. So I mean, it's kind of close enough, I guess, because we also had to do other resistors in there as well. So you can tell that this requires more voltage than a 5 volt can supply. But if we go back to red, again, I'm just a hobbyist. I'm not really a electronic engineer, but the point is you can check for like the roundabout. You can get the voltage drop from all the LEDs right here. You can check out how many resistors there are per LED diode, and from there you can just get the voltage, see what these are. There's calculators online where you can just say how many LEDs I have, and what the supply voltage is, and it'll tell you and what's the voltage drop for all the LEDs, and that will tell you what resistance values you need. So there's a couple tools out there, and I'll probably put a link in the description to show you guys how to do that. But I mean, this is just kind of a brief overview. I mean, there's also, can't forget about the damn connectors, damn it. So the connectors can vary quite a bit. The best way to do it is to get a connector, and the best way to find out like what type of connectors you need, like for example this. Get like a caliper, and you measure it. You know, that's kind of the best way to do this. Again, you have to do a little bit of searching, and like, you know, a way to verify is look at the data sheet. So if you just like if you kind of find a connector that looks like it. I mean, I think this is a Pico GST connector right here, and Gigabyte seems to use them a lot. And this right here is also this right here is, these two are also Pico. This is a Pico, so these are compatible with each other. This has a Pico GST as well, and so right here is JST PH. This is for like the Gigabyte WindForce. That's what I use these for. Looks like Gigabyte used a lot of GST Picos for their headers. This one on the back, I have no idea what it is. It's very, very, very small. So who knows? Might look that one up, I might not. I mean, this board is like dead, so I'm not gonna really mess with it a little bit any more than that. But I mean, you just use calipers, look up, you know, see if there's a JST, you know, one that looks similar, and if you know if it's a JST Pico or PH or, you know, SM, or like all the different numbers and letters that they have put together, just try to measure it and look up a 4-pin JST PH and a data sheet, and the data sheet will show exactly the measurements and compare it to what you measure with calipers, and you can find, you know, if it's correct or not. I mean, that's kind of the best way to do it. I mean, it's these, you know, it's one thing for, you know, your RGB headers. I mean, they're fairly standard these days, but you know, every manufacturer might use a different one. I mean, I'm seeing 4 different connectors, if you include that one, for just Gigabyte alone between the WindForce, this board, and this board. Yeah, So I mean, you kind of have to do a little sleuthing, and I know some people will be really up for this and other people won't. Well, thank you very much. If you have any questions, I'm sure you will. Feel free to post it. I appreciate you putting up with this for this long. I mean, it takes a lot to go into this, and I probably missed a few things, so who knows, I might do a follow-up video on this, things I've missed in my previous video. But feel free to subscribe if you like this and want to see more content like this. Thank you again for Mod My Mods for lending me this board, and Gigabyte for giving them this board so I could test it out. And Mod My Mods and probably Pirate Tech would probably be happy to make you a cable, potentially. You'd have to talk to them. I'm not going to promise anything, but you know, I did a soldering video, and you know, you can try soldering. There's plenty of videos on crimping out there, and I'm not the best crimper, so feel free to look on guides like that on how to actually make the little cables instead of just, you know, kind of just doing proof of concept and, you know, your breadboard tests. So again, if you have any questions, feel free to post them. Thank you very much. Feel free to subscribe.